Welcome to my tutoring session in chemistry. In this video, I'll explain the principles involved in paper chromatographic separation method. The current video is part 1 of the two-part series in paper chromatography. I'll explain the stationary phase and mobile phase used in paper chromatography, the principle used in the paper chromatographic separation, the surface modified Whatman paper, detection methods and applications of paper chromatography. What is chromatography? Chromatography is a separation technique where the given sample mixture is separated into individual components using a stationary phase and a mobile phase. Let's say we have a sample mixture S and our objective or goal is to separate the given sample mixture into individual components. And this can be accomplished by employing the chromatographic separation technique. Now the given sample mixture can be separated into individual components A, B and C using a stationary phase and a mobile phase. A stationary phase is a non-moving phase. It stays put during the experimentation, while the mobile phase is a moving phase and it moves over the stationary phase during the chromatographic separation process. So chromatography is a separation technique where the given sample mixture is separated into individual components using a stationary phase and a mobile phase. What is paper chromatography? Paper chromatography is a separation technique where the given sample molecule is partitioned between two liquids based on its relative solubility or affinity. The molecule is partitioned between two liquid phases, of which one is a stationary phase. Now stationary phase here is a liquid. It refers to the water layer that is adsorbed to the cellulose layers in the Whatman paper, while the other liquid phase is the mobile phase that moves over the stationary phase during the separation process. Now in the Whatman paper, the water layer is adsorbed over the cellulose layers in the filter paper and that acts as a stationary phase. Now Whatman paper is available in different shapes and sizes. Mobile phase, which is a moving phase, it is a liquid solvent of varying polarity. So Whatman paper is commercially available in different grades like grade 1, 2, 3, 4 and so on. And these Whatman paper grades commercially available, they differ from each other in terms of porosity and thickness. So it is the porosity and thickness of the Whatman paper that leads to their grading. Of all the available grades in the market, the grade 1 is the most widely used filter paper. Now grade 1 Whatman paper is available in different shapes and sizes. They are available in the form of circles of suitable dimension and also in the form of sheets. Now Whatman paper is made up of cellulose. And what is this cellulose material? Cellulose is a polymer. It is a polysaccharide where the D-glucose units are held together by 1,4-beta glycosidic linkage. Now this cellulose layer in the Whatman paper, you will find a water layer adsorbed on the surface of the Whatman paper. And this water layer acts as a stationary phase. And over this Whatman paper, a sample is applied on the baseline. And when the Whatman paper with applied sample on the baseline, when it is placed in the chamber for development, you can see that the mobile phase, it travels through the Whatman paper by capillary action. Now the sample is sandwiched between the stationary phase and the mobile phase, and during the development process, the sample moves at varying speeds and their relative moment depends on its relative affinity towards the stationary phase. When the sample has greater affinity towards the stationary phase, it travels a shorter distance. When the sample has lesser affinity towards the stationary phase, it travels a longer distance. Now there are 4 prerequisites for carrying out the paper chromatographic experimentation. They are a solid support, which is cellulose of Whatman paper, a stationary phase, that is the water layer that is adsorbed on the cellulose layer of the Whatman paper, the sample that is applied over the Whatman paper. Now the sample, it could be an individual compound or it could be a multi-component sample mixture that is applied on the baseline, and a mobile phase, which is a liquid solvent which flows over the stationary phase by capillary action. And during the flow of the mobile phase over the stationary phase, the sample also moves. So the movement of the sample depends on its relative affinity towards the stationary phase. So we have a stationary phase, which is a water layer adsorbed on the cellulose layer of the Whatman paper. A baseline is drawn at the lower end of the Whatman paper, which is around 1 to 2 centimeters. And a reference line is drawn at the top of the Whatman paper for the solvent print. Now the sample is applied on the baseline, and the mobile phase, it travels through the Whatman paper by capillary action, and in the process the sample also moves. So the movement of the sample depends on its relative affinity towards the stationary phase. So the principle of separation for paper chromatography is partition. Now the separation of the molecule is based on the partition between 2 liquids, of which one is a stationary liquid while the other is a mobile liquid, which is flowing through the stationary phase. So the principle of separation for paper chromatography is partition. So what is this partition coefficient? Let's try and understand the meaning of partition coefficient with a simple experimentation involving extraction of the drug molecule highlighted as red spheres between 2 immiscible liquids. One is octanol, the other is water. So partition coefficient is ratio of solubility of the substance or molecule between 2 immiscible liquids at constant temperature. Now the drug molecule here in this case is highlighted as red sphere, while the 2 immiscible liquids are octanol and water. And the partition coefficient is represented by letter P. Now in the first case, you'll find that the drug molecule, it has equal affinity for both the layers. you can find 5 molecules in the water layer and 5 molecules in the octanol layer. So there is equal distribution of the drug molecules between the two layers, octanol and the water layer. And therefore, and how do you calculate the partition coefficient? You can calculate the partition coefficient by dividing the concentration of drug in octanol upon the concentration of drug in water. So here you find 5 molecules in water and 5 molecules in octanol. So that will be 1. So partition coefficient is 1. And when this happens, when you try and carry out the separation using paper chromatography, you will find that this spot is somewhere at the center, indicating that this molecule is of intermediate polarity. Now in the second case, you will find that 10 molecules are in the octanol layer while only 1 molecule is in the water layer. And partition coefficient is around 10. So this is because greater affinity for the drug molecule towards the octanol layer. It is more soluble in the octanol. And when you try and separate this molecule by paper chromatography, you will see that the spot for the drug molecule, it has traveled a longer distance because it is less polar and it is more soluble in the octanol layer, which is a non-polar liquid. So like dissolves like. So when the molecule is non-polar in nature, it tries to dissolve in the non-polar octanol, and therefore it is dragged during the separation process at a longer distance. Now in the third scenario, you will find that 10 drug molecules are in the water layer while there is only 1 molecule in the octanol layer. And this clearly shows that the drug molecule has greater affinity for water layer with a partition coefficient value of 0.1. So 1 by 10, that is 0.1. So what will be the chromatographic profile in this case? Now here you will find that the drug molecule is more soluble. It has more affinity in the water layer. So it is more soluble in the water layer and therefore it travels a shorter distance. And remember, this water layer is adsorbed over the cellulose layers in the Whatman paper. So in paper chromatography, the molecule of interest is partitioned between 2 liquid phases. One is the stationary phase, where the water layer adsorbed over the cellulose in the Whatman paper acts as a stationary phase, while the other is the mobile phase, which moves over the stationary phase. And in the process, the molecule of interest gets separated. So in paper chromatography, the molecule or the mixture being separated, it gets partitioned between 2 liquids. One is the mobile phase, other is the stationary phase. So in partition chromatography, you find distribution of molecules between 2 liquids, like in case of paper chromatography. So when the molecule is more soluble in the water layer, it travels a shorter distance. And what about adsorption chromatography? In contrast to partition chromatography, in case of adsorption chromatography, you will find the distribution of molecules between solid and liquid, where the mobile phase is again a liquid, while the stationary phase, it is a solid, like in case of polar solid silica. Now silica is polar in nature because of the polar silanol groups, where the hydroxy groups are covalently bonded to the silicon. And the molecule that is being separated, it is held together strongly by the stationary silica layer by hydrogen bonds. So in case of partition chromatography, you find distribution of molecules between 2 liquids, That is, the molecule is getting partitioned between two liquids. While in case of adsorption, you will find that the molecule is getting adsorbed over the stationary phase by means of hydrogen bonding. So adsorption is a surface phenomenon. That is why you find the molecules clinging onto the surface of the stationary phase by non-covalent interactions or non-covalent interactive forces like hydrogen bonding. So the principle of separation in partition chromatography is the separation based on partition between two immiscible liquids. One acts as a stationary liquid, other is a mobile liquid. Whereas in case of adsorption chromatography, separation is based on adsorption of the molecule on the surface of the solid station. Now, Whatman paper is made up of cellulose. Cellulose is a polymer. It is a polysaccharide where you find the D-glucose units held together by 1,4-glycosidic linkage. And a water layer is adsorbed on the surface of chromatographic paper, which acts as a stationary phase. And in the water layer, you will find that these water molecules are held together by hydrogen bonds. And why does this water layer stick on to the cellulose layers in the Whatman paper? Again, it is the hydrogen bonding which is holding the water layer over the Whatman paper. And the mobile phase, it moves over the stationary phase. And in the process, the molecule is getting separated between the stationary phase and the mobile phase. Now let's compare and contrast the relative movement of 4 amino acids, that is glycine, alanine, tyrosine and phenylalanine. Now glycine is a highly polar molecule. It travels a shorter distance. Alanine, less polar compared to glycine. It travels further. Tyrosine is non-polar because of the benzene ring. It travels further. While phenylalanine, which is the most non-polar molecule, it travels a longer distance in comparison to these 3 amino acids, as it is non-polar in nature. Now the relative movement of these 4 amino acids depends on its relative affinity towards the stationary phase. Now where does this affinity come from? This affinity comes from non-covalent interaction. So glycine is strongly held by hydrogen bonds with the water layer. Likewise in case of alanine. But alanine has traveled a distance further in comparison to glycine because it is slightly non-polar because of that methyl group. While tyrosine, because of the aromatic ring, it is non-polar in nature. It travels further ahead despite the hydrogen bonding interaction. While the phenylalanine has traveled a longer distance because of its lesser affinity towards the liquid phase. So the van der Waals attraction between the tyrosine and phenylalanine is what drags the molecule further. So there are two forces in operation here. One is the hydrogen bonding, other is the van der Waals attraction. Now the partitioning of the amino acids or any drug molecule between the stationary phase and the mobile phase can be explained with respect to the stationary phase as well as the mobile phase. With respect to the stationary phase, the movement of the components is governed by the relative affinity towards the stationary phase. When the molecule has greater affinity towards the stationary phase, it travels a shorter distance, and the molecule with greater affinity, that is lesser affinity, it travels a longer distance. And with respect to the mobile phase, the molecule which is more soluble in the mobile phase travels a longer distance, like in case of phenylalanine, while the molecule which is less soluble in the mobile phase, it travels a shorter distance. And that is how the 4 amino acids glycine, alanine, tyrosine and phenylalanine they get separated into individual components due to their partitioning between the stationary phase and the mobile phase. So sample is applied on the baseline, and remember this sample is a multi-component mixture made up of glycine, alanine, tyrosine and phenylalanine. And after the separation, you find that these four components or amino acids, they travel or cover a different distance because each amino acid has a different affinity towards the stationary phase. So two forces are governed or governing the separation process. One is the hydrogen bonding, other is the van der Waals attraction. Now there are three types of paper chromatography, and they are classified based on the surface modification of the Whatman paper. So classification is purely based on the stationary phase or the nature of the stationary phase. In the first type, paper partition chromatography, where the water layer adsorbed over the cellulose layers in the Whatman paper acts as a stationary phase, which we have discussed. The second is the paper adsorption chromatography, where the paper is impregnated with silica or alumina, which is used as a stationary phase. And third is the hydrophobic fibers, which can be prepared by acetylation of cellulose, and that can be used for reverse phase chromatography. So Whatman paper is made up of cellulose, and cellulose is a polymer. It is a polysaccharide where the D-glucose units are held together by 1,4-glycosidic linkages. On acetylation, you will see that the hydroxy groups in the D-glucose units, they are getting acetylated, and the hydrogen atom is replaced by the acyl group, making the cellulose non-polar. So after the acetylation reaction, the cellulose is converted into cellulose acetate, which you call it as the acetylated Whatman paper. Now the acetylated Whatman paper or cellulose acetate, it is non-polar in nature because all the polar OH groups are blocked by the acyl groups. And this non-polar cellulose acetate, it can be used for separation of non-polar substances like steroids. And this will be mechanism. And this mechanism is based on reverse phase chromatography. So why it's called reverse phase? Because in normal phase, the stationary phase is polar, like in case of cellulose. So in reverse phase, the polarity changes. The polar cellulose is converted into non-polar cellulose acetate. So once the polar surface is made to non-polar, it can be used for separation of non-polar or lipophilic substances like steroids by reverse phase chromatography. Now cellulose of Whatman paper, it can also be impregnated with thin layer of silica. And one more method, the cellulose of the Whatman paper can also be impregnated with alumina layer, thin film of alumina layer. And silica and alumina papers prepared in this fashion are used for separation of less polar substances like amines, vitamins, triglycerides and steroids. So polar substances can be separated by using silica and alumina papers because the stationary phase is polar in nature. Now before you begin the paper chromatography experiment, make sure that you saturate the chromatographic chamber, and this can be done by filling the chromatographic chamber with the mobile phase of interest that you have selected for the separation process, and close the chamber. Set aside for a short period of time whereby the chamber is completely saturated with vapors of the mobile phase. And now the chamber is ready for the development process. That is for the paper chromatography experiment. So meanwhile, you can prepare the Whatman paper. So when the chamber is getting ready for the preparation, that is the separation process, you can prepare the Whatman paper. Cut the Whatman paper to suitable dimension, and you can hang the paper using a siphon glass rod. Draw a baseline at the lower end of the Whatman paper. Apply the sample over the reference spot and keep it ready. Now the Whatman paper can also be hung using a thread. Now the chamber is ready for the experiment. Remove the lid. Introduce the prepared Whatman paper, which is hung using a thread. Close the chamber, and you can see that the mobile phase, it travels to the Whatman paper by capillary action, and in the process the given sample mixture gets separated into individual components. When the separation is done with saturation of the chamber, you end up with a very good separation. When you carry out the separation without saturating the chamber, you will end up with edge effect. Now, when you do not carry out the saturation of the chamber, it results in a bad separation. It results in edge effect. Now, what is this edge effect? Now, in the edge effect, you will find that the solvent at the center has traveled a greater distance than the solvent at the edges. And when this happens, the path at which the components travel, they are disturbed, they are disoriented, and therefore the components tend to travel either towards the left side or towards the right side, and that affects the actual distance traveled by the component, and you will end up with wrong RF values. So saturation of the chamber is a must, and this is to avoid the edge effect. And how do you select the solvent system, and what is the criteria or basis for selecting the solvent? The selection of the solvent or the mobile phase depends on the nature of the substance to be separated, that is whether the substance to be separated is polar or non-polar in nature, or it is of intermediate polarity. Second factor is nature of stationary phase, whether the stationary phase is polar or non-polar, and the mode of chromatography, whether we are following the normal phase or the reverse phase method. So the sample mixture is separated into individual components, and they travel with different speeds, and this depends on the relative affinity of the components towards the stationary phase. The glycine G, it has traveled distance x1, alanine, it has traveled distance x2, tyrosine has traveled distance x3, and phenylalanine has traveled distance x4. And the mechanism or the reason why they travel at varying distances is already been explained. And when you are trying to calculate the distance traveled by the component from the, during the separation process, you have to consider the center of the spot. Always consider the center of the spot when you are trying to measure the distance from the baseline. Now let's say you are given a sample mixture. The sample mixture is abbreviated as S, which is a multi-component mixture made up of 4 amino acids: glycine, alanine, tyrosine, and phenylalanine. Glycine is abbreviated as G, alanine as A, tyrosine as T, and phenylalanine as P. And the usual concentration of the solution is around 1%. Take a sheet of Whatman paper, cut into suitable dimension. Draw a baseline at the lower end of the Whatman paper using pencil. And this baseline should be around 1 to 2 centimeters from the lower end of the Whatman paper. And draw a reference line at the upper end of the Whatman paper, and it should be around 0.5 to 1 centimeter from the top of the Whatman paper. And this is a reference line for the solvent front. Now I would recommend the beginners in carrying out the separation by paper chromatography to draw the reference line for the solvent front, because you should know when to stop the experimentation. When the solvent front has reached this particular reference line, you have to stop the separation process and remove the paper from the chromatographic chamber. Apply the sample on the baseline, and the diameter of this spot should not exceed 3 millimeters. So ideally it should be around 1 to 2 millimeters. And the volume of solution should be around 2 to 5 microliters of a 1% solution. And how do you control the addition, or how do you add the samples? Now samples can be applied using either a microsyringe, micropipette, or a capillary. So good addition can be achieved using microsyringe, micropipette, or a capillary. Now addition by using droppers is not recommended, as the addition cannot be controlled. So addition of the sample solution can be effectively controlled by using microsyringe and micropipettes. If microsyringe and micropipettes are not available in the laboratory that you work in, you can always use the capillary, which is very cheaper. So the given sample mixture is separated into individual components, and they travel at different speeds because of their relative affinity towards the stationary phase. And the mobile phase, it travels to the paper by capillary action, and it flows against gravity. And when the solvent front has reached the reference line for the solvent front, you can stop the separation process, remove the Whatman paper from the chamber, and dry the paper using a dryer. Now measure the distance traveled by the solvent from the baseline. Let's say y is the distance traveled by the solvent from the baseline. Let's say it is 5 centimeter. X1 is the distance traveled by glycine. X2 is the distance traveled by alanine. X3 is the distance traveled by tyrosine. And X4 is the distance traveled by phenylalanine. So always measure the distance traveled by the components from the baseline, considering the center of the spot. Now the glycine, it has traveled a shorter distance because of its more affinity towards the stationary phase. While phenylalanine, it has traveled a longer distance because of its lesser affinity towards the stationary phase. Now the stationary phase here in this paper chromatography experiment is the water layer adsorbed onto the cellulose layers of Whatman paper. Mobile phases, butanol acetic acid combination. Now let's try and calculate the RF value for glycine, that is abbreviated as G. So RF value, it can be calculated using the formula distance traveled by the sample divided by distance traveled by the solvent from the baseline. So X1 is the distance traveled by glycine from the baseline. Let's say it is 1 centimeter, and 5 centimeters is the distance traveled by the solvent from the baseline. So 1 by 5 will be 0.2. So RF value for glycine is 0.2. Likewise, you calculate the RF values for alanine, tyrosine, and phenylalanine. Now remember, the RF values, it varies depending on the combination of the mobile phase or the mobile phase that you are using for the experiment. So as you vary the ratio of butanol acetic acid composition, the RF values may also vary. So RF value is abbreviation for retardation factor or retention factor. It is used for qualitative analysis. It is used for identification purpose. And RF value is specific or a constant value for the given molecule or a chemical compound. and it is constant for a given combination of stationary and mobile phase. The amino acids in this experiment, they travel at different rates up the paper due to their different solubilities in the two phases. Now coming to now the separation is done. We have separated the given sample mixture into individual components and we have dried the paper. But the problem is we are not able to visualize the separated components. And that is where the detection methods or visualization methods come into picture. Now the visualization or detection methods for colorless compounds is purely based on the chemical method. We are using the chemical for visualizing the colorless spots, and you make use of visualizing spray reagents. So for our experimentation, the given sample mixture, which is made up of glycine, alanine, tyrosine and phenylene, is applied on the baseline. Around 2 to 5 microliters of 1% solution of the sample mixture is applied on the baseline, and make sure the diameter of the spot should not exceed 2 to 3 millimeters. Now when the components that are being separated, if they are naturally colored or if the compounds, if they have their color of their own, then life is made easier for the person or a chemist who is carrying out the separation. So visual assessment of the chromatogram can be done easily, and you can easily identify the spots and calculate the RF values immediately. So visual assessment of the chromatogram is made easier if the compounds are colored. The problem is when the components being separated are colorless, when they do not have any characteristic color of their own. And that is where the detection methods come into picture. So now what you do, you spray this paper with a ninhydrin reagent. So ninhydrin reagent is a recommended reagent for visualizing the amino acids. It is recommended reagent for detection of amino acids for the chromatographic experiment. On spraying, you can see that purple spots are developed. Now purple spots is a result of chemical reaction between ninhydrin and amino acids. And here is the chemical reaction between ninhydrin and amino acid. So the amino acid chemically reacts with the ninhydrin reagent that is sprayed over the paper, and this results in a purple pigment. So the purple coloration is because of reaction between the amino acid and the ninhydrin. Now what are the applications of paper chromatographic separation method? There are several applications and I have highlighted one of the important ones. Paper chromatographic technique, it can be used for the separation and identification of polar compounds like dyes, analgesics, antibiotics, amines, amino acids, alkaloids, glycosides, sugars, vitamins and pharmaceutical drugs. This separation method, it can also be used for detection of impurities and assessment of purity of the compound. Detection of adulterants in foods and drinks can also be done, and the analysis of cosmetics can also be carried out by this method. Both qualitative as well as quantitative analysis can be performed. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.